English for engineering.
Tiếng Anh ngành kỹ thuật.
8.1.
We know the client is a very green-orientated company, very big on all things environmental.
Absolutely.
So energy saving obviously needs to be an important consideration in the design. Clearly, it's a big subject and something we need to look into in depth. But one specific aspect of it where I think we can make a real difference is with the building management system. Specifically, with the way we use presence detectors. And I've had a couple of ideas that I'd appreciate your views on.
Sure.
I think we should put two totally different design options to the client. Option one is to have a building with maximum automation. So, with the maximum automation option...
8.2.
With the maximum automation option, we put presence detectors all over the place and link them to as many systems as possible. Not just the usual systems that activate the lights when people walk into rooms and turn them off when they leave. We could use presence detectors to control other systems as well, like the blinds on the windows. So, if it's the middle of summer and a presence detector senses that everyone's left a meeting room, a temperature sensor picks up a positive reading from sunlight coming through the glass. The electronics activate the blinds, which automatically come down and black out the room. That would limit heat absorption and reduce the load on the air conditioning, saving energy.
Okay.
Or in winter, if the blinds had been pulled down in the meeting room the evening before, the next morning the sensor detects sunlight and triggers the blinds to raise and let in as much sunlight as possible, contributing to the heating. And there could be temperature measurements to determine which rooms are the warmest, and those sensors set off a circulation system to distribute the warm air through the building, into the corridor or into rooms at the other side of the building or wherever.
So we'd use presence detectors and heat sensors to regulate as many systems as possible?
Yes. Well, that's what we'd have with the maximum automation option.
8.3.
The second option is this. It's a very environmentally conscious company, so I assume that green attitude is shared by all the staff. If that's the case, why is there a need to automate everything in the building when most things can be operated manually? Why doesn't the boss just circulate an email reminding people to switch the lights off when they go out and tell them to lower the blinds when they leave a room in summer so it helps the air conditioning? I mean, you'd save electricity because you wouldn't need to control all the systems automatically, and the money you saved by buying old-fashioned manual controls instead of high-tech electronics could be spent on planting trees or something. I mean, it sounds simple, but...
It's a very interesting idea. We have to bear in mind, of course, that the client's a manufacturer of high-tech electronic gizmos. I'm not sure how they'd feel about this in the long term.
8.4. 1.
The obvious danger here is that you could get a build-up inside the vessel if there's a blockage further along the pipe.
So the vessel needs a safety valve?
Yes, and maybe some sort of warning system as well. It could be something that's triggered by a differential measurement. So if there's a higher reading in the tank and a lower one further along, you'd know there was a blockage somewhere.
2.
We'll need a system for monitoring gas consumption.
What, a meter on the supply pipe?
Well, yes, that would measure cumulative consumption. But we also need to monitor the actual rate of consumption at different points in time during the reaction cycle. And if we have those two parameters, we can then determine the frequency of peaks in consumption, which is the third parameter we need.
So that's a software issue then. As long as the cumulative value is being recorded against the timescale, we can plot the rate of consumption against.
3.
The reaction that takes place is going to be exothermic, but the amount of heat will partly depend on how hot the gas is when it enters the vessel.
Yes, because that input heat can be adjusted.
Exactly. So we'll need a sensor next to the valve to measure the input value as gas comes in, and then another to give us an output value. Then we can work out the optimum input temperature for the gas.
8.5.
One of the biggest headaches in power generation is the fact that electricity consumption fluctuates considerably. So in order to maintain a continuous supply, we have to make continual checks and adjust the power load we generate. To help us plan those adjustments, we forecast fluctuations in demand so that we can anticipate peaks and troughs. We base these forecasts on a number of different factors. One of them, one of the most important ones, is temperature. During periods of very cold or very hot weather, demand increases. The increase in demand is obviously due to millions of electric radiators coming on when it's cold and air conditioning units working hard when it's hot. Another factor, a key factor, which increases or decreases demand is whether or not it's light or dark in the morning and evening. Obviously, that dictates lighting consumption. So those are the two main seasonal factors. They generally go hand in hand, so on cold, dark winter evenings, the rise in demand is significant compared with warm, light summer evenings. We also take into account what day of the week it is, particularly whether it's a weekday or the weekend. Generally, demand rises during the week, when factories and offices are operational, and then decreases when a lot of them close at the end of the week. So demand falls at the weekend. Those are variations that take place within a given week. During any given day, there are factors such as meal times, when electric ovens are switched on. Obviously, that causes a jump in consumption. Even commercial breaks during popular TV shows can cause blips in demand. There can be a sudden rise when people rush to switch kettles on or heat up snacks in microwaves, and then a sudden fall shortly afterwards.
8.6.
Because electricity consumption fluctuates across a significant range, in order to cope with peak demand, our maximum capacity is equivalent to the top of that band of fluctuation. That means that during off-peak periods, we have significant spare generating capacity. Now, in an ideal world, it would be good to use that spare capacity to generate power and store it for use during peak times. Unfortunately, as you probably know, electrical charge is extremely difficult to store in large amounts. You can't just charge up huge batteries. So we use an innovative technique to store up power potential during off-peak periods.
8.7.
The concept of pumped storage is relatively simple. During off-peak periods, when main power stations have got spare capacity, some of the extra power they produce is used by pumped storage stations to pump water from a low-level reservoir up to a high-level reservoir, where the water's stored. It's then held there until there's a peak in demand at some point the next day. At that point, the water's released, and it flows down the pipes, driving turbines at the bottom, which generate electricity. Obviously, the station can only run for a fairly short period, but it's sufficient to cover the peak in demand. Then, as soon as there's a dip in demand, the water can be pumped back up and held ready for use again. So the effect is to smooth out fluctuations in the output of the main power stations. Some of the main station's spare capacity is used when there would be a trough in the demand curve at night. The peak daytime generating capacity of those main stations can also be lower because the pumped storage stations are there to back them up when there are blips in the demand curve.
8.8.
Questionnaires like this drive me mad. I mean, look at this first question. What percentage of my time do I spend doing technical tasks that use my skills extensively? How are you supposed to put a number against that?
You only need to give a ballpark figure.
I know, but even so, it's difficult to say off the top of my head.
It's easier if you compare it with the second option.
Doing tasks that a less qualified colleague could do. Well, let's say roughly half and half.
Are you sure? Aren't you the least qualified person in this department?
Do you know, I knew you were going to say that. Number 2. technical tasks that add value and tasks that don't add value, such as admin. Add value? What's that supposed to...
Well, do you not do some admin, or do you spend all of your time doing productive things?
Well, no. Nowhere near all of it.
Right, so is it 50-50?
Well, no. I spend more time problem-solving than I do on admin, thankfully. Let's say somewhere in the region of 2/3. So about 1/3 on admin. 3. Tasks that are purely technical versus tasks that relate to technical organisation. Well, most of what I do is organisation, isn't it? I spend pretty much all my time on that.
Or in your case, disorganisation.
Nice one. What figure did you put down for added value, by the way? Was it a negative number?
8.9.
At this stage, I'm not asking you to give me a detailed breakdown of all the IT equipment we're going to need. It would just be useful to have a rough idea of what's most urgent.
Sure, well, one of the biggest problems is the screens at the CAD stations. A lot of those need replacing with bigger ones. Roughly speaking, I'd say well over half of them are too small. A good 2/3 of them, actually, so we're talking about 15 to 18 screens, something like that.
Okay. How urgent is that?
Well, I mean, they all work. They all function properly. The trouble is, the engineers spend the vast majority of their time working with these screens. And because the detail on them is so small, it's pretty hard work on the eyes, to the point that it affects productivity, so...
Okay, and what about the big printer in here? I've heard it's a bit of a dinosaur.
Well, it is, but it works perfectly well, and we print next to nothing with it anyway. Most of the drawings are printed at the factory.
Ngoại ngữ chuyên ngành.com